Okay, so this problem is about a block being launched by a spring. So we've got a 100 cube, 100 gram cube. It's is launched by pulling a spring back 12 centimeters and released. The spring constant is 65 newtons per meter. And so what is this cube's launch speed? So we need the launch speed as it leaves the spring. And we see that the surface is frictionless. So we have our given, so our before and our after. And so notice that the 0 position is when the block leaves the spring, and the initial velocity is 0. So we're pushing this block against the spring this way. So we're pushing the block this way here and compressing the spring, and then the spring will push the block forward until it's no longer touching, and that will be its initial velocity. So what we're going to do is we're going to use the work energy theorem. So back here. So let's think about our free body diagram. So we've got a free body diagram, and we know we have the force of the normal, and we have the force of gravity, and they're equal, right? And then we have the force of the spring. And so this is the spring is acting on the block. So what we know is we know then that the sum of the forces is equal to is going to equal an acceleration, and we know what are the sum of the forces. So this sum of the forces here is F net, and so the only force we have acting in the x direction is the spring force. So our F net is F spring. And so when we think about the object moving, our object is moving only in the x direction. So if we want to think about work is equal to our F spring, and remember it's dotted, the dot product of delta R, but our case, right, our delta R, it's the block is only moving in the x direction. So we're going to have W, or work, is equal to, since F and delta x are in the same direction, then our dot product is just the magnitude of the two multiplied together, delta x. And so we know that the force, this is the force of the spring here. And so we know that W is going to equal, we need to use the integral now because our F spring is, it varies with x. So we're going to have an integral of a negative k x dx from x initial to x final. And so if we want to write that out a little bit more, we're going to have a negative k, and then we're going to have x dx from a negative 0.12 meters to 0 meters. So we're saying that this position right here, this is at 0, and our x initial is at a negative 12 meters. Okay, so we want to do this integral out. We're going to get a negative k x squared over 2, right? That's the integral of x dx. And we're going from a negative 0.12 meters to 0. And if we plug that in, we're going to have work is equal to a negative k over 2. And plugging in, we're going to have 0 squared minus negative 0.12 meters squared. So W is equal to K is a negative, so we're going to have 1/2. Our negatives here, negative in front, negative here, and our negative here cancel. So we get a positive work, and we're going to have 65 newtons per meter. And we're multiplying that by 0.12 meters squared. And when we do the math, we get work is equal to 0.468 Newton meters. We're going to relate this to energy, to our kinetic energy. So delta K is equal to our work. And we have delta K is 1/2 m, and this is delta V squared is equal to work. And we know that delta V is equal to V final minus V initial. In our case, V initial is 0. So we're going to have 1/2 m V final squared is equal to work. So we're going to multiply both sides by 2. So multiply by 2. And we're going to divide by m. So I'm going to multiply by 2 and divide by m. So I'm going to have V final squared is equal to, these can't, these cancel, so I get 2 work W over M, and so V final is the square root of 2W over M. I plug numbers in, so I get V final is equal to 2 times 0.468 Newton meters divided by kilograms, square root, divided by, let's see, 0.1 kilogram. So V final, when I plug the numbers in, I get 3.1 meters per second squared, meters per second. So that's my answer. So that is the velocity that the block, when it's no longer touching the spring, right here at, right here, when it's no longer touching the spring, it'll have a velocity of 3.1 meters per second.